Climate change is a change in the statistical distribution of weather patterns when that change lasts for an extended period of time. Climate change may refer to a change in average weather conditions, or in the time variation of weather around longer-term average conditions. Climate change is caused by factors such as biotic processes, variations in solar radiation received by Earth plate tectonics, and volcanic eruptions. Certain human activities have also been identified as significant causes of recent climate change, often referred to as global warming. Scientists actively work to understand past and future climate by using observations and theoretical models. A climate record, extending deep into the Earth's past, has been assembled, and continues to be built up, based on geological evidence from borehole temperature profiles, cores removed from deep accumulations of ice, floral and faunal records, glacial and periglacial processes, stable isotope and other analyses of sediment layers, and records of past sea levels. More recent data are provided by the instrumental record. General circulation models, based on the physical sciences, are often used in theoretical approaches to match past climate data, make future projections, and link causes and effects in climate change. Terminology. The most general definition of climate change is a change in the statistical properties of the climate system when considered over long periods of time, regardless of cause. Accordingly, fluctuations over periods shorter than a few decades, such as El Niño, do not represent climate change. The term sometimes is used to refer specifically to climate change caused by human activity, as opposed to changes in climate that may have resulted as part of Earth's natural processes. In this sense, especially in the context of environmental policy, the term climate change has become synonymous with anthropogenic global warming. Within scientific journals, global warming refers to surface temperature increases, while climate change includes global warming and everything else that increasing greenhouse gas levels will affect. Causes. On the broadest scale, the rate at which energy is received from the sun and the rate at which it is lost to space determine the equilibrium temperature and climate of Earth. This energy is distributed around the globe by winds, ocean currents, and other mechanisms to affect the climates of different regions. Factors that can shape climate are called climate forcings or forcing mechanisms. These include processes such as variations in solar radiation, variations in the Earth's orbit, variations in the albedo or reflectivity of the continents and oceans, mountain building and continental drift, and changes in greenhouse gas concentrations. There are a variety of climate change feedbacks that can either amplify or diminish the initial forcing. Some parts of the climate system, such as the oceans and ice caps, respond more slowly in reaction to climate forcings, while others respond more quickly. There are also key threshold factors which, when exceeded, can produce rapid change. Forcing mechanisms can be either internal or external. Internal forcing mechanisms are natural processes within the climate system itself. External forcing mechanisms can be either natural or anthropogenic. Whether the initial forcing mechanism is internal or external, the response of the climate system might be fast, slow, or a combination. Therefore, the climate system can respond abruptly, but the full response to forcing mechanisms might not be fully developed for centuries or even longer. Internal forcing mechanisms. Scientists generally define the 5 components of Earth's climate system to include atmosphere, hydrosphere, cryosphere, lithosphere, and biosphere. Natural changes in the climate system result in internal climate variability. Examples include the type and distribution of species, and changes in ocean currents. Ocean variability. The ocean is a fundamental part of the climate system, some changes in it occurring at longer time scales than in the atmosphere, as it has hundreds of times more mass and thus very high thermal inertia, with effects such as the ocean depths still lagging today in temperature adjustment from effects of the Little Ice Age of past centuries. Short-term fluctuations such as the El Niño Southern Oscillation, the Pacific Decadal Oscillation, the North Atlantic Oscillation, and the Arctic Oscillation, represent climate variability rather than climate change. On longer time scales, alterations to ocean processes such as thermohaline circulation play a key role in redistributing heat by carrying out a very slow and extremely deep movement of water and the long-term redistribution of heat in the world's oceans. Life affects climate through its role in the carbon and water cycles and through such mechanisms as albedo, evapotranspiration, cloud formation, and weathering. Examples of how life may have affected past climate include glaciation 2.3 billion years ago, triggered by the evolution of oxygen ice photosynthesis, which depleted the atmosphere of the greenhouse gas carbon dioxide and introduced free oxygen. Another glaciation 300 million years ago, ushered in by long-term burial of decomposition-resistant detritus of vascular land plants. Termination of the Paleocene-Eocene thermal maximum 55 million years ago by flourishing marine phytoplankton. Reversal of global warming 49 million years ago by 800,000 years of Arctic azolla blooms. Global cooling over the past 40 million years driven by the expansion of grass-grazer ecosystems. External forcing mechanisms, orbital variations. Slight variations in Earth's orbit lead to changes in the seasonal distribution of sunlight reaching the Earth's surface and how it is distributed across the globe. There is very little change to the area annually averaged sunshine, but there can be strong changes in the geographical and seasonal distribution. The three types of orbital variations are variations in Earth's eccentricity, changes in the tilt angle of Earth's axis of rotation, and precession of Earth's axis. Combined together, these produce Milankovitch cycles which have a large impact on climate and are notable for their correlation to glacial and interglacial periods, the correlation with the advance and retreat of the Sahara, and for their appearance in the stratigraphic record. The IPCC notes that Milankovitch cycles drove the Ice Age cycles. CO2 followed temperature change, with a lag of some hundreds of years, and that as a feedback amplified temperature change. The depths of the ocean have a lag time in changing temperature. Upon seawater temperature change, the solubility of CO2 in the oceans changed, as well as other factors impacting air-sea-CO2 exchange. Solar output. The sun is the predominant source of energy input to the Earth. Other sources include geothermal energy from the Earth's core, and heat from the decay of radioactive compounds. Both long and short-term variations in solar intensity are known to affect global climate. 3 to 4 billion years ago, the sun emitted only 70% as much power as it does today. If the atmospheric composition had been the same as today, liquid water should not have existed on Earth. However, there is evidence for the presence of water on the early Earth, in the Hadean and Archean eons, leading to what is known as the faint young sun paradox. Hypothesized solutions to this paradox include a vastly different atmosphere, with much higher concentrations of greenhouse gases than currently exist. Over the following approximately 4 billion years, the energy output of the sun increased and atmospheric composition changed. The Great Oxygenation Event, oxygenation of the atmosphere around 2.4 billion years ago, was the most notable alteration. Over the next 5 billion years, the sun's ultimate death as it becomes a red giant and then a white dwarf will have large effects on climate, with the red giant phase possibly ending any life on Earth that survives until that time. Solar output also varies on shorter time scales, including the 11-year solar cycle and longer-term modulations. Solar intensity variations, possibly as a result of the Wolf, Sporer and Maunder minimum, are considered to have been influential in triggering the Little Ice Age, and some of the warming observed from 1900 to 1950. The cyclical nature of the sun's energy output is not yet fully understood. It differs from the very slow change that is happening within the sun as it ages and evolves. Research indicates that solar variability has had effects including the Maunder minimum from 1645 to 1715 AD, part of the Little Ice Age from 1550 to 1850 AD, that was marked by relative cooling and greater glacier extent than the centuries before and afterward. Some studies point towards solar radiation increases from cyclical sunspot activity affecting global warming, and climate may be influenced by the sum of all effects. Interestingly, a 2010 study suggests that the effects of solar variability on temperature throughout the atmosphere may be contrary to current expectations. In an August 2011 press release, CERN announced the publication in the Nature journal the initial results from its cloud experiment. The results indicate that ionization from cosmic rays significantly enhances aerosol formation in the presence of sulfuric acid and water, but in the lower atmosphere where ammonia is also required, this is insufficient to account for aerosol formation and additional trace vapors must be involved. The next step is to find more about these trace vapors, including whether they are of natural or human origin. Volcanism. The eruptions considered to be large enough to affect the Earth's climate on a scale of more than 1 year are the ones that inject over 100,000 tons of SO2 into the stratosphere. This is due to the optical properties of SO2 and sulfate aerosols, which strongly absorb or scatter solar radiation, creating a global layer of sulfuric acid haze. On average, such eruptions occur several times per century, and cause cooling for a period of a few years. The eruption of Mount Pinatubo in 1991, the second largest terrestrial eruption of the 20th century, affected the climate substantially. Subsequently, global temperatures decreased by about 0.5 degrees Celsius for up to 3 years. Thus, the cooling over large parts of the Earth reduced surface temperatures in 1991 to 93, the equivalent to a reduction in net radiation of 4 watts per square meter. The Mount Tambora eruption in 1815 caused the year without a summer. Much larger eruptions, known as large igneous provinces, occur only a few times every 50–100 million years, through flood basalt, and caused in Earth past global warming and mass extinctions. Small eruptions, with injections of less than 0.1 amount of sulfur dioxide into the stratosphere, impact the atmosphere only subtly, as temperature changes are comparable with natural variability. However, because smaller eruptions occur at a much higher frequency, they too have a significant impact on Earth's atmosphere. Seismic monitoring maps current and future trends in volcanic activities, and tries to develop early warning systems. In climate modeling, the aim is to study the physical mechanisms and feedbacks of volcanic forcing. Volcanoes are also part of the extended carbon cycle. Over very long time periods, they release carbon dioxide from the Earth's crust and mantle, counteracting the uptake by sedimentary rocks and other geological carbon dioxide sinks. The U.S. Geological Survey estimates that volcanic emissions are at a much lower level than the effects of current human activities, which generate 100 to 300 times the amount of carbon dioxide emitted by volcanoes. A review of published studies indicates that annual volcanic emissions of carbon dioxide, including amounts released from mid-ocean ridges, volcanic arcs, and hotspot volcanoes, are only the equivalent of 3 to 5 days of human-caused output. The annual amount put out by human activities may be greater than the amount released by super-eruptions, the most recent of which was the Toba eruption in Indonesia 74,000 years ago. Although volcanoes are technically part of the lithosphere, which itself is part of the climate system, the IPCC explicitly defines volcanism as an external forcing agent. Plate tectonics. Over the course of millions of years, the motion of tectonic plates reconfigures global land and ocean areas and generates topography. This can affect both global and local patterns of climate and atmosphere-ocean circulation. The position of the continents determines the geometry of the oceans and therefore influences patterns of ocean circulation. The locations of the seas are important in controlling the transfer of heat and moisture across the globe, and therefore, in determining global climate. A recent example of tectonic control on ocean circulation is the formation of the Isthmus of Panama about 5 million years ago, which shut off direct mixing between the Atlantic and Pacific Oceans. This strongly affected the ocean dynamics of what is now the Gulf Stream and may have led to Northern Hemisphere ice cover. During the Carboniferous period, about 300 to 360 million years ago, plate tectonics may have triggered large-scale storage of carbon and increased glaciation. Geologic evidence points to a mega-monsoonal circulation pattern during the time of the supercontinent Pangaea, and climate modeling suggests that the existence of the supercontinent was conducive to the establishment of monsoons. The size of continents is also important. Because of the stabilizing effect of the oceans on temperature, yearly temperature variations are generally lower in coastal areas than they are inland. A larger supercontinent will therefore have more area in which climate is strongly seasonal than will several smaller continents or islands. Human influences in the context of climate variation. Anthropogenic factors are human activities which affect the climate. The scientific consensus on climate change is that climate is changing and that these changes are in large part caused by human activities, and it is largely irreversible. Science has made enormous inroads in understanding climate change and its causes, and is beginning to help develop a strong understanding of current and potential impacts that will affect people today and in coming decades. This understanding is crucial because it allows decision-makers to place climate change in the context of other large challenges facing the nation and the world. There are still some uncertainties, and there always will be in understanding a complex system like Earth's climate. Nevertheless, there is a strong, credible body of evidence, based on multiple lines of research, documenting that climate is changing and that these changes are in large part caused by human activities. While much remains to be learned, the core phenomenon, scientific questions, and hypotheses have been examined thoroughly and have stood firm in the face of serious scientific debate and careful evaluation of alternative explanations. United States National Research Council, advancing the science of climate change. Of most concern in these anthropogenic factors is the increase in CO2 levels due to emissions from fossil fuel combustion, followed by aerosols and the CO2 released by cement manufacture. Other factors, including land use, ozone depletion, animal agriculture and deforestation, are also of concern in the roles they play, both separately and in conjunction with other factors, in affecting climate, microclimate, and measures of climate variables.